Right, good morning everyone. So we continue our painful adventure with potential flow. But hopefully at least you will see why it's useful. So today I'm going to focus on what we call building blocks for potential flow. And hopefully you will appreciate certain things and why they are useful and some of the key concepts related to this. Right. So I'm going to talk about uniform flow, which we all know. Sources and sinks you haven't seen before. Vortex flow maybe. We're going to talk about a dividing streamline. I don't think I will have time to talk about flow around the flow circular cylinder. We can leave that to next time. So what we want you to learn is what are the building blocks for potential flow. How would you recognize what we call a dividing streamline? And as I said later, to recognize what is a potential flow around a circular cylinder. So let me just kind of put you back in the picture and try to, in doing so, trying to revise what we've been saying. So remember guys that potential flow by definition means two things. So it's inviscid, means we are ignoring the effect of viscosity. So we're saying, if we're talking about air for example, we're just saying the viscosity is absolutely zero. We know that's not true because viscosity is there. Also we're saying the flow is irrotational. Anyone remembers the property that tells us something is rotational or not? You guys remember? James? Starts with V, not velocity. Vorticity, very good. Yeah, so the vorticity is basically the cross product of delta times V. And if the vorticity is zero, it means the flow is irrotational. What do I mean by that? It's very important to understand what irrotational. It refers to the fluid elements, whether they are rotating about an axis, which is moving with them, okay? So if they rotate around their own axis as they go along, that is a rotational flow. If they don't, they just maybe translate, but they don't rotate. They just for example, translate. That is an irrotational flow. So it's really linked to if the fluid elements are actually rotating as they move along. If they don't, that's irrotational. So that's potential flow. And actually, if you read around, you will find that a truly inviscid flow will lead to an irrotational flow anyway, okay? But that's what potential flow is. So you can see it's a simplification. Now we can add another simplification, which is to say, can we say the flow is incompressible, which means we ignore the changes of density. Density is constant. So as you guys can see, we made all these simplifying assumptions, which makes our model the simplest possible model you can get for a fluid flow, okay? Right, now much of the theory for potential flow is actually developed hundreds of years ago, I'm afraid. But you can imagine mathematicians at that time who were working on trying to describe how the flow motion is mathematically, using mathematical equations. They didn't have these tools you guys have now, NSYS and all these CFD tools. Obviously, it was not available. So they were doing their best to try to describe how the flow actually behaves. So, and of course, at that time, we didn't have any aerospace industry, okay? Everyone was, the big power at that time was ship power, isn't it, all right? If you had a fleet of ships and you're very powerful, it's equivalent to having all these military might at this time in terms of aerospace. So, obviously, some of the work was on ships and design of ship hulls and stuff. So, and of course, the water goes around the ship. So, mathematicians basically were trying to describe that motion using mathematical equations, and they had to come up with a list of those simplifications, i.e. the potential flow. So, it actually originates from hydrodynamics. It's not truly aeronautic one. So, potential flow However, despite being all those simplifying assumptions, it's actually quite useful in real situations as well. It's not like completely useless. And particularly if you're talking about flow away from a solid boundary, okay? More scientifically, away from the boundary layer. So if it's away from the boundary layer, it is actually, although it's a physical flow, we can actually approximate it rather accurately with a potential flow model. However, if you are modeling the flow inside the boundary layer, where there is a lot of viscosity inside the boundary layer, that's why we have the boundary layer in the first place, then it is impossible to try to model the boundary layer using a potential flow. You just get nonsense, all right? So I always say to students, if you go to a large aerospace company and one of the interview questions is, how would you model the flow around the wing? In the boundary layer, you say, I can use potential flow. I don't think they will hire you, to be honest. So it's very important to understand that. Potential flow, we said that potential flow can be described in two ways. Either using the tool of the stream function psi, or using the velocity potential phi, okay? So they're just mathematical descriptions. And the first property you guys should remember is that they're both orthogonal to each other, all right? So they're at 90 degrees. So if you plot them, they will always be at 90 degrees to each other. So what is so useful about this stream function and velocity potential? Well, you can actually, if you describe them, you can actually get the velocity components, which is actually of most importance to us. And we said that for the potential flow, the velocity in 2D, we're talking about 2D, the u component of the velocity field is the derivative of phi with respect to x, and v is the derivative of phi with respect to y. I know it's partial derivative, but it's exactly the same idea as derivative. So, and in terms of the stream function that are given by these, we've seen these equations before. So now we know what are the velocity components, which is, we're getting there somewhere, so it's very good. But that's not enough. Then the great Bernoulli equation can be used by knowing from knowledge of the velocity field, you can get the pressure field. Well, that's even a more improvement now. So we're getting more information. And from the pressure field, because if you know the pressure field, you can actually get the forces around the body, which is ultimately what we want. Particularly things like the lift on a wing, for example. Okay, so this is how it works. You start with psi and phi, get the velocity components, and then get the pressure field using Bernoulli's. If you know the pressure field, you can get the forces. So this is how it works. So it's quite a neat way in doing that. We also said potential flows, they satisfy the Laplace equation. Namely, the second partial derivative of phi or psi is equal to 0. So that's Laplace equation by definition. Laplace equation is also linear, and therefore we can add solutions together to get more complex solutions. If we start with something simple and another something which is simple, add them together, you create something a little bit more complex. That complex thing is also a solution of the Laplace equation. It satisfies the Laplace equation. That's the great thing, is it allows us to add solutions to get something more complicated, as I will show you. So what I'll try to do today, I'll do my best, is really to tell you that the key idea in potential flow is that if we start from very simple models that are potential flow models themselves, of course, we can actually create rather complex flows around, real bodies, and basically we can approximate real flows in real life. So, what are these elementary or basic potential flows? The first one is uniform flow. I will show you that. Second one is the sort and sink, and lastly is the vortex flow, actually, the free vortex flow. So these are kind of the building blocks. And I want you to think about it in a very simplistic way. Guys, when you buy those games and you put things together, right? You got the building blocks, right? But you have to put them together to get something more complicated. It's exactly the same with potential flow. So let's go through these elementary flows one by one and see if we combine them, what actually can we get? And that hopefully shows you why potential flow can be useful.